Hello all. It's been on my mind lately that a lot of trainees and/or people learning fire protection design don't really understand the hydraulic nodes they have on their drawings from calculations. We all understand that they're a reference, but why are they some places and not others? This becomes a bigger factor with 99% of calculations being done by programs like AutoSprink and SprintCAD that automatically generate nodes, and sometimes they generate nodes that have no purpose, confusing reviewers. The trainees, not knowing why nodes are put at certain places, don't see the problem as it's happening, and it can result in a costly resubmittal depending upon the HJ. So the node is a reference point for the drawing sheets to link up with the calculation sheets, but where do they go? Simply put, they go anywhere where the friction loss per foot changes or goes through a curve adjustment. But what changes the friction loss? For that, we just need a basic understanding of the values that factor into the Hazen-Williams formula. Flow, inside diameter of pipe, and C-factor. Anytime one of these changes, it results in a change in the amount of loss across a cumulative pipe length and equivalent length segment. A common misconception is that there should be a node anytime the flow changes direction, but a change in direction of flow doesn't change the flow itself, and as seen in NFPA 13, a 9D or a T just needs the properly associated equivalent length added. Most valves also fall into this category. We'll talk more about the exceptions towards the end. Let's look at three factors we listed. First off, we had flow, which is the biggest contributor since the other two can actually be mathematically converted to even out, something you just can't do for flow. Anytime we add flow, we are increasing our friction loss across pipe length. So that means that any heads flowing in a remote area add flow and thus get nodes, as well as any open hose connections and/or allowances. This also changes where flows combine, such in loops or grids. These nodes make up the bulk of our reference points. The second factor we listed was internal pipe diameter. Since a change in this number changes the way the equation plays out, points of change should have their own node designation. Commonly, these are remote area branch line connections to cross main connections to a standpipe, and base of riser connections. There will be other locations as we manipulate our pipe sizes to achieve safety factors, but these are the most common. The third thing we listed was C-factor, which behaves much like inside diameter, but tends to change much less often, typically only between a system header and the dry pipe it serves, and a systems connection point to the incoming underground. The last thing is something we briefly touched on, valves. But valves aren't just a standard adjusted equivalent length. We're talking about devices that have their own loss or gain curves. By saying they have a curve, we are saying that they have a different pressure loss impact depending upon the flow, so it can vary from calculation to calculation. With a variable such as that, it often makes sense to have a node so that it's easy to compare the calculated loss to the official device information's loss chart. This also applies to things with the negative loss, e.g. fire pumps. A pump's pressure boost changes depending on the flow, but a pump itself doesn't add flow. It simply increases downstream pressure dependent upon the flow. Since the pressure is vastly different at the pump suction and the pump discharge, a node should be associated with each. All these put together, and your system with nodes should look roughly like this example of a multi-story building with standpipe and pump. The nodes for the head in the remote areas, the nodes for the accumulation of the remote area's flows, the nodes for a change in size to a cross main, the node for a change in size to the standpipe, the node for addition of inside hose allowance, the node for a change in pipe size at a concentric reducer, nodes for both the discharge and suction flanges, a node for the backflow preventer for the loss curve, a node for the connection to the underground pipe, a node for the change in underground pipe sizes, and finally a node for the tested supply point, the origin of our flow. I hope this video helps you figure out what the nodes on your drawing are telling you, and when you should manipulate what a program is reading so that it gives you a cleaner and more concise drawing.